Welcome back, everyone. In the last video, we introduced arrays. We saw how we can define an array, such as an array of integers, using syntax like int scores, and then the size of the array inside these square brackets. And this will define an array called scores that has enough room for 3 integers. We then learned how we can insert values into this array by indexing into the array's locations, and we saw that we could go to the first location or the first index of this array using scores square bracket 0, and then scores square bracket 1 to get the next, and scores square bracket 2 to get the last. We looked at how this would be represented in the computer's memory as 12 contiguous bytes, which is enough to store 3 integers that each take up 4 bytes. We also used a loop to loop over the locations in this array, and then to insert a value at each location. Finally, we saw how we can pass a whole array as an argument to a function, and saw some slight optimizations that we can use to make our program better designed. If you haven't watched part 1 on arrays, make sure you check that video out first so that you have a better understanding of everything that we're going to be covering in this one. So in this video, we're going to be continuing our discussion on arrays and ultimately build up to explaining what a string actually is, so that we can start to solve problems using text. Instead of working with integers this time, let's simplify a bit and take a look at simple chars. Chars, of course, only take up 1 byte, so let's suppose that we have these 3 lines of codes. And albeit I hope that you can see at this point that this isn't the best design, because we have these 3 variables that look pretty much the same. But notice that each of these variables is a char. They're called C1, C2, and C3, and each has a character as a value, wrapped in single quotes. And if we consider what this looks like in the computer's memory, it's going to look like this. C1 might end up here, C2 might end up here, and C3 might end up here. And again, this is just an artist's rendition of our computer's memory. If there's other stuff going on, then these 3 variables might end up at different locations in the memory, but they're going to be taking up 1 byte each. We've introduced ASCII in previous videos, so we understand that letters like H, E, and Y are represented using this mapping of numbers to letters. So what's really being stored here are the number equivalent of 72, 69, and 89. And if we looked at the binary representation of these numbers, we would see this. And again, chars use 1 byte. 1 byte is 8 bits, and so each of these will be represented using 8 bits, which is enough to store these small numbers from 0 to 255. The point here is that we don't have to use 4 bytes to store these small numbers. We can use a different data type, like chars, and under the hood it will use 1 byte to store these values. So that's great, but this isn't really how we've been implementing strings. Like when we wanted to store the user's name in a variable, we did something like string name and then assigned the value Chris in double quotes. And you can imagine that if we had to define a different variable for each character in our strings, this would get incredibly tedious. So we keep talking about these things called strings, and up to this point, I've defined strings as a sequence of characters inside double quotes. But now that we understand arrays, we can start to take these training wheels off a bit. We'll see soon that strings aren't exactly what they seem to be, but for now the key thing is that strings take up a variable length of bytes. If we have hey, it would take up 3 bytes. If we had the string Chris, it would take up 5 bytes, because each character uses 1 byte. We've already seen that we can define a variable of type string using the following syntax. We can provide the data type string, then provide a name to this variable. I'll just call this S for now because it's just a simple string that we're going to be using as an example. And finally, we can assign a value to this string, like hey in double quotes. And now let's take a look at what this looks like in the computer's memory. And I would propose that following what we've learned so far, it might end up looking like this. We have one variable called s, and it takes up 3 bytes, 1 byte per character. And in C, when you define a string like hey, the bytes will be contiguous, or back to back to back. So now that you see this visual representation of a string, you might be able to infer what a string actually is. Like, what is a string if this is how it's laid out in our memory? Well, it's just an array of characters. And we can treat strings just like we would an array. Technically, a string called s is really a variable called s that allows you to get to the first location with s bracket 0, and the next location with s bracket 1, and the final location with s bracket 2. You can literally get individual characters in a string using this newfound syntax for arrays, which a string actually is underneath the hood. But there's a catch. How do we know where the string ends? When we used ints, we know that they take up 4 bytes. When we used longs, we know that they take up 8 bytes. But how many bytes does a string take up? Well, again, it depends on the string. This one of hey takes up 3 bytes, but a string like Chris would take up 5 bytes. But where do we put the 3 or the 5? Like, this is literally all that's in your computer. So the catch is that we need a way to determine how long a string actually is. And this can be solved in a couple different ways, but the way that the creators of C decided to solve this was to add 1 extra byte to the end of each string, just to make clear that this is the end of the string. So under the hood, anytime you define a string, you will get your string like hey, and the compiler will add this special value at the end of the string called the null terminating character. And we represent this character using \0. In reality, it's just 8 0 bits, or a byte of all zeros, and it's generally called null, N-U-L. We've actually seen this, although we didn't point it out, but if we bring back our ASCII chart from a previous video, you can see up here in this top left corner, represented by 0, is actually null, N-U-L. So when you define a string in your code that is 3 characters long, like H-E-Y, what's actually being stored in your computer's memory is H-E-Y followed by this \0, because the compiler knows to add this special character at the end of each string. So technically, a 3-character string uses 4 bytes. A 5-character string, like Chris, would use 5 plus 1 or 6 bytes total. In fact, if we convert these back to integers again, we can see that it's literally 72, 69, 89, and 0 being stored in our computer's memory. And C is smart enough to know that when you print out a string, it will print each character until it gets to this \0 or this null character, and then it will stop. More specifically, printf knows how this works, and this is how printf knows when to stop printing a string. This all happens automatically for you, but it's important to understand that strings in C are just arrays of characters that end with \0. Let's see some examples in code that will prove this, and we'll see if we can get a better understanding of what's actually going on in our computer's memory. I'm here in my Ubuntu virtual machine, and let's open up a terminal. We'll change directory into tutorials, and we'll use code dot to open up VS Code in this directory. I'll close out of this file from last time and save it. I'll come in here and create a new file. We'll just call this hey.c. And let me do my boilerplate of #include stdio.h, int main void, curly brackets, return 0, and let me just define a couple variables in here. I'll say char c1 is equal to h, char c2 is equal to e, char c3 is equal to y. And then let me just print this out with printf. I can't use %s because these three variables are literally characters, because that's how I've defined them. But I could do %c, %c, %c. We'll add a new line, and then let's pass in c1, c2, and c3. And if we save this and open up the terminal, we can compile this with gcc-o, hey, and hey.c. And then if we run /hey, it appears that we've implemented a string, albeit using this very verbose and frankly stupid syntax of defining a different variable for each character in this string. What's cool though is that now that we know that characters are just numbers and strings are just characters, we can start to poke around in the computer's memory. What if I changed all these placeholders to %i? And we'll put a space in between these just for aesthetics. Now if I save this and come recompile and rerun, you see that we get the integer equivalents of these characters that I claimed were actually being stored underneath the hood. These format codes just tell printf how it should display these values. %c tells printf to display them as characters, while %i tells printf to display them as integers. But again, this isn't how we define strings in C. We've been using strings, the data type. So instead of these three variables, let's do string s is equal to hey. And just know that when we use strings, we have to include the CS50 header file for now. And we'll eventually see why, but for now, let's come up in here and include cs50.h. And now since s is in fact a string, I can use a single %s right here, and we can just print out s. And if I save this and I come recompile, but again I have to add this -l cs50 since I'm using the cs50 header file. And if I run with /hey, we still get our hey. And this is nothing new. But now that we understand that strings are just arrays of characters, we could technically come in here and let me print out a %c and not pass s, but pass s bracket 0 for the first location in this array. And I'll save, come in here and recompile, rerun, and we get just our h. I could then come back down here, we'll print out another %c, another %c, and we'll pass s bracket 1 and s bracket 2. I'll save this, come recompile, rerun, and we still get our hey. And all we've done is print it out manually by passing each of these characters to printf and printing them as a character. And again, I could change these to %i. I'll put a space, %i, %i, save this, and come recompile and rerun, and we get our 72, 69, and 89. And if I got a little more curious, maybe I come in here and put another %i. We'll pass s bracket 3. Save this, recompile, rerun, and we see that we actually get to see that \0 or the null terminating character, which again is just 8 0 bits. So this is just revealing what's going on underneath the hood. Let's ramp this up a little bit and get a deeper understanding of strings and arrays. Instead of just having one string of hey, let's create another string. We'll just call this string t, and we'll assign the value by. And instead of printing all this, let me just pass in s and a %s, and then I'll printf I'll do another %s, another \n for a new line, and this time we'll pass t. So nothing new, I'm just defining these two string variables and printing them out. But now if we look at the computer's memory, we know that HEY \0 will be in these first 4 bytes, and BYE \0 will probably end up right next to it in memory. But these are just regular variables, so there's a chance that they're separated. However, we have this \0 to delineate where one string ends and another string starts. So let's come back into our code and let's see something new. If I have these two strings of S and T, let's put them in an array. So instead of these two strings, I can say string words {2} to define an array called words that has enough room for 2 strings. And then I can assign some values to these array locations. I can use words {0}, get to the first location, and I'll assign the value hey. I can then come to words {1), and I'll assign the value bye. So now this is pretty much the same as our example from the last video when we created an array of ints. But this time we're creating an array of strings. And now if I want to print the first word in this array called words, I can use %s and pass in words {0). And then to print the second word, I can use words {1). And this isn't the most useful program, but it's just to show how we can start to tinker around a bit. What I can do is I can come down here and instead of printing %s to get the whole string, let me use %c, %c, %c to print out all 3 of the characters in this first word. And if we know that words is an array of strings, and strings themselves are just an array of characters, we can use words {0} to get to the first word in the array, and we can use the same logic to get to the first character in the first string. So I can use words {0} to get to the first character. I can then use words {0} {1} to get to the next character, and words {0} {2} to get to the last character. And now down here, words {1} is the second string in this array. So I can do %c, 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 and we'll do words {1} {0} to get the first character in the second word, then words {1} {1) to get the next, and words {1} {2) to get the final. So this is crazy syntax. Like, this isn't how we're going to be programming. This is just for demonstration, but just reassures what I'm proposing of how these are being represented in the computer's memory. Let's save this and open up the terminal, recompile, and rerun, and we see that we get HEY and then BYE by printing the first character in the first word, second character in the first word, and the third character in the first word, and the same for bye. But let's take one final look at how this is represented in our memory. We have this single array that we can call using just words. However, this array has 2 strings in it, and we can get to the first one using words {0), or we can get to the second one using words {1). We can also go a bit deeper, and we can get at each individual character in each word using these double square brackets. Words {0) is this first string, and the first character in the first string is at {0). The second character is at {1), and so on. And our second string starts at words {1), the first character being at {0), the second being at {1), and so on. So I know that this has been a lot, and these concepts are starting to become a bit more complicated, but feel free to ask questions, and I encourage you to play around with these concepts as much as possible. Try things and then reach out if something doesn't make sense to you. I hope you found some value in this video. If you did, make sure you hit that like button to show your support and to show that you want to see more content like this in the future. In the next video, we'll take a look at a couple more concepts around arrays and strings and see some examples of why this is useful. I appreciate all the support and I hope to catch you in the next video.